Okay, so now we're going to start the new material for this semester. So this starts the beginning of new material. The last two sections were just review. We're going to need those to do a lot of our integrals. So it's important that we have those down pat. So this section is section 6.1. It is areas between curves. So the idea behind this section is, before when we were talking about integrals, we were talking about, I want to find the area underneath a curve, maybe like this. Maybe I'll use a different color. So I want to find, this area. And what this is, if this is f of x, then the way I find this area is b is the integral from a to b f of x dx. Now the question becomes, what if I don't want to find the area from, curve to the x-axis? What if I have instead, I can use the same color. So what if I have two curves that look like this? So this is f of x, this is g of x. Let me move g. So let me move that down here. This lower one is g of x. And what if I want to find instead the area between these things? So you can look in the book. So you can look in the book, and the book goes through the Riemann integrals. So starting with the sum, and then changing it into a integral by taking the limit. I'm not going to go through that because it's pretty obvious what we're going to do here. So what we're going to do is, if I look at this, I'm going to draw this picture again. So it's not going to be exact, but let's say it looks something like this. And the way I'm going to, let me redraw that because it's going to make it really hard to show what I'm talking about. So let's stay over here. So let's say I want to find the area between these two curves. If I look at the, so let's use red for f of x. If I look at the area for f of x here, this is, so the area for f of x is all that stuff. And the area for g of x, let's use blue, in this region is this. So g of x looks like this. So you can see what we want here. I'm going to mark it. I'm going to mark it. We want this area inside here. And you can see is, if I can get, so if I take the integrals and I get these two things to cancel out, this is the place I want to get rid of. So if I can cancel these areas out, then I'll be left with only the area inside here. So the way I'm going to do that is, if you look at this, so f of x here, in this case, it's all positive. But I want to end up subtracting off, what g of x contributes. And I also want this whole thing to be positive. So I want this, so the reason I want it to be positive is because I'm trying to figure out the total area of this curve. So what I'm doing when I do that is I'm taking the integral, and I'm taking, the area underneath f of x, and I'm subtracting off the area underneath g of x. This is the area between curves. So all I do, and notice here, f of x is the top function. And g of x down here is the bottom function. So it's always going to be top minus bottom, and you're going to integrate that. The only other thing that you're going to run into issues with is you might have to figure out what your bounds of integration are. That's going to be where these two things intersect. So we're going to see how to do that in a second. So let's do an example. So we need to find the area between the region bounded above by y is equal to e to the x, and bounded below by y is equal to x, and bounded on the sides by x equals 0 and x equals 1. Okay, so let's draw a picture just so we can see what's going on. All right, so I have y equals e to the x. It's going to look like that. Y equals x. It's going to look like sorry, I've drawn that wrong. E to the x, sorry, starts at 1. So I was getting confused about. It goes off like that. Y equals x is going to look something like this. And let's say this is x equals 1 here. So we're going to draw a line there, and x equals 0. So I'm interested in, the area inside here. And don't get tripped up by, bound on the sides by 0 and 1. You can see that I'm just trying to find the area inside here. So let me draw that a little more expanded. So what this looks like is I have that. I have this thing, and then this. So what this is, I have my top function e to the x here. I have my bottom function x. Starts at 0, ends at 1. And that gives me the entirety of what I'm trying to find as an integral. So the area between these two curves is going to be the integral from 0 to 1, the top function minus the bottom, dx. So this is the integral. So the top function is e to the x minus x and dx. And again, my values are from 0 to 1 here. And that's it. So now it just becomes a problem of evaluating this, and we've done this before. So it's actually not too bad. I'm just creating these new functions that somehow represent the area between these curves. So if I do this integral, I'm going to get e to the x minus x squared over 2, evaluated from 0 to 1. And so what this ends up being is, so if I plug in 1, I'm going to get e minus 1/2 minus e to the 0 minus 0. And if I do all this, this is e minus 1/2 minus 1. This is e minus 3/2. And that's my answer. There's really no simplifying that. So we're going to leave it like that. So one thing you'll notice is they gave us the bounds for integration, x equals 0 and x equals 1. We're going to see an example now where that doesn't happen. So we're going to have to determine the bounds of integration by ourselves. So let's do that example. So I have find the area enclosed by the parabolas y is equal to x squared and y is equal to 2x minus x squared. So picture always helps. And during this stuff, you're allowed to use a graphing calculator if you want to see what's going on here. Okay, so if you draw this, so they actually both, so let's do this, and then we have x squared looks like this. And what I'm trying to find now is this area in here. Let me label my functions here. So the upside down parabola is obviously the 2x minus x squared, and the right side up, really poorly drawn parabola, that one's x squared. And that kind of tells you what my bottom and top functions are. So you can see that the 2x minus x squared is my top function. But now I need to figure out my integration bounds. So you can kind of see that they are the same at 0. So they both intersect at 0. What I'm trying to find here is I'm trying to find the intersection points here and here. So the way we figure out where two things intersect, the way we figure out where two functions intersect, so you have to think about what we're asking. We're asking, where do these two functions have the same value? Where are the two functions equal? And that's what we're going to do. We're going to set the functions equal in order to figure out what the intersection points are. We're going to solve this for x. So we set equal for intersection points. Now we solve for x. So if I, let's add everything over. So we're going to have 2x squared. Well, so 2x squared minus 2x is equal to 0. You can divide everything by 2. X squared minus x is equal to 0. This factors pretty easily. X times x minus 1 is equal to 0. I have x equals 0. X equals 1 for the intersection points here. Block this off because I'm going to keep writing on the right-hand side here. And now I can set up my integral. So remember, my integral is going to be the integral from the intersection points, let's call them a and b, of the top function minus the bottom function, dx. So again, we've already identified the top. The top here is this one. It's the 2x minus x squared. We know what a and b are now. It's 0 to 1. And then we're going to have 2x minus x squared. And the bottom function is x squared, dx. So now when I simplify this, this is 1 minus 2/3 when I plug in 1, minus 0 minus 0. So this is 1 minus 2/3, which is 1/3. So the area between those two curves is 1/3 of a unit, whatever we're doing. So again, just kind of a recap. It was easy to figure out once we drew it what the top curve and what the bottom curve was. In this case, so unlike the first example, we had to figure out what our integration bounds were. And for that, you're just figuring out where the two functions intersect. And to do that, you set them equal. You get the integration bounds, and then you integrate the function top minus bottom. So pretty straightforward. So let's move on to the next example. Okay, so we're gonna move on to another question. So, so before, all of our graphs looked really nice. They looked like this, and I was trying to find that area there. But the question becomes, what if I have something that looks like this? So let's say it goes like that, and then G goes like this. And I want to find I want to find these two areas. So let's call this one f of x. Sorry. This one here is f of x. And then, so that one's that. This one here is g of x. So what you'll notice here is that, you know, f of x is not always the top function, and g of x then is not always the bottom function here. So g of x, so actually this first area on the left here, g of x is the top function, f of x is the bottom function. Second one in the second area here, f of x is the top function, g of x is the bottom function. So, you know, if the question becomes, how do we find this area here? Well, it's actually not too difficult. So what you'll do is you'll integrate, you know, over the first region, over the first area, where you do g of x minus f of x. And then when you get to this area here, you'll switch. You'll do f of x minus g of x for that area. So this can all be summarized in this. So the area between two curves, f of x and g of x, between x equals a and x equals b, is given by the integral from a to b, absolute value of f of x minus g of x dx. And the reason we can write this is because, remember, the definition of absolute value of f of x minus g of x, this is going to be f of x minus g of x when f of x is greater than or equal to g of x. Then it'll be g of x, so just a minus sign, g of x minus f of x when f of x is less than g of x. So by writing it like this, it automatically takes care of, you're always doing the top minus the bottom function. So you'll see that in case one here, f of x is the top function because it's greater than g of x. We're doing f of x minus g of x. In the second case here, g of x is the top function because it's greater than f of x. So we're doing g of x minus f of x. So I'm going to stop the recording here, and then I will go on to an example where we do this. I just don't want to go over too much time with this. So I'll stop now and move on.